So today we will go through the design of steel structure elements for combined action and portal frames. So combined actions mean that we have, for example, normal and bending moment. This normal force may be compression or tension forces, which is the case in the portal frame. Because as you know, any portal frame, the column or the beams are subjected to moment, for example, something like that, and also normal, for example, like that. So this is normal and this bending moment. So when you design the column or the beam of a portal frame, it is subjected to combine the action of normal and bending moment. Okay. In this week, we are talking about like because the beam also we have some parts of the beams with full lateral strain and without full lateral strain and action or beam columns or portal frames. Okay. In this week, I will go through the equations. First, you can read this stuff just to save some time. Okay, so here is the first part of our calculations. So these are the calculations. So we are looking at the member capacity of segments restrained against displacement and rotation, and could be not. And this will affect the member lateral restraint because if it is lateral restraint, so no lateral buckling will happen or will occur. But if lateral buckling could occur or will occur if no lateral restraint. Okay.
The members or the beams with full lateral strain will not be subjected to lateral buckling. So no lateral buckling due to the laterally restrained. Okay. But if there is no lateral buckling, no lateral strain, so the lateral torsional buckling will occur. This lateral torsional buckling will affect the member capacity of our beams. That's why we need to consider the lateral restraint in our calculations. So if we want to determine the member capacity of segments with full lateral strain, according to the Australian standard 4100, so the nominal member capacity of a segment shall be taken as the nominal section capacity MS. So M member capacity equal to M section capacity for members with fully lateral strain. Okay. This is what we learned last week in the flexure design or bending moment design for beams, that MS is the section capacity. Okay, so the nominal section capacity according to the Australian standard is MS equal to F yield times Z effector, where the effective section modulus ZE shall be or can be calculated using clause 523, 524, or 525. Okay, so to know the section capacity, we need to find the section slenderness lambda E, which categorize the member to compact, non-compact, and cylinder. So we have 3 types of member according to the cylinderness ratio. So according to these 3 types, that's why we have 3 clauses to find MS, or the section capacity. Okay, to find lambda E or lambda effective, we have this formula here. So lambda E equal to B over T root F yield over 250. Okay, where B and T thickness of web or flange, and B is the width of flange or height of web. As you know, if we have a steel member here, so for flange, this is T flange, and this is what we are looking at to calculate the cylinderness ratio, which is B flange minus T web over 2, where this is T flange again, and this is T web. For web, we need this height D. So for web, D is B for web, and T web is T for web. Okay, so using this formula, we can know if the web or flange is compact, non-compact, and cylinder. Okay, and we need to know if it's compact or non-compact or cylinder. We need to compare lambda E with lambda E yield, or lambda EY, which is the plate element yield cylinderness according to table 5.2. So to know if the section is compact or cylinder or non-compact, you need to compare lambda E with lambda E yield. Okay, if lambda E more than E yield, so the section will be compact. If less, it will be cylinder. And we need also to compare lambda E plastic, lambda EB. So these cases are, you can revise it in the previous lecture. And now, and so finally for this one, for any member with fully lateral restraint, the member capacity MB equal to the section capacity MS equal to F yield times Z effective. This is the main thing in the previous point. The second part today, or this is the most important, this is the important one today with the beam column. So beams without fully lateral restraint. So in this one, the beam is subjected to or vulnerable to lateral buckling. So in this part, we have firstly segment fully or partially restrained at both ends. So we have the first case, segment are laterally restrained at both ends. But it is not lateral restrained in the span itself. So if you have a beam like that, let's say this is an I-beam here. So you have support here and support here, and have the span. So at this two support, the beam is laterally restrained. But in the middle, there is no lateral restraint. So the beam is allowed or susceptible to buckle in this direction, out of the plane like this. Okay, so this what is mean in for the first case. So in this case, for open section, which is like UC or UB sections, as we know, with equal flange, we have to apply the following. So for segment of constant cross section, the member capacity MB is as follows. So this is the member capacity of beams without lateral restraint, but restrained at both ends. So MB equal to lambda M, lambda S, MS, and should be less than or equal to MS, which is the section capacity. So MS from the previous section is section capacity. That's why I have added the first part of this lecture, because we need to know MS here. So lambda M is a moment modification factor. Lambda S is the slenderness reduction factor. MS is the nominal section capacity determined in accordance with clause 5.2 for the gross section, which is MS equal to F yield times Z effector. So here, as you can see, lambda M can be taken as 1 or as a value obtained from table 5.61 or from this formula. Lambda M equal to 1.7 M over M2 star squared, M3 star squared, M4 star squared. And lambda M cannot be more than 2.5. Okay, so you can take alpha M as 1 or from table 5.6 or from this value. Let's go to this table. So if we go to this table here, so this is table 5.6.1, moment modification factor alpha M for segments fully or partially restrained at both ends. These are some few cases for this. So this is the beam segments. This is the beam segments, different type, like 2 end moments, 2 concentrated load, 1 concentrated load, 1 concentrated load and moment, like uniform load with end moment, uniform load with 2 end moments, and here is cantilever, and here is cantilever with cantilever with concentrated load, cantilever with a uniform load. Okay, this column here give us lambda M, which for example here for member with concentrated load, this is lambda M, where A is the distance from the center line of the beam to the load, L is the span of the load of the beam, so this is L. So you can find alpha M. Okay, so this for example about the table. The other value of lambda of alpha M is 1.7 mm, where mm is the maximum design bending moment in the segment. So if we have beam like this is the moment. So this is BL over 4. So the maximum moment here is BL over 4. M2 and M4 are design bending moment at the quarter points of the segments. So quarter points mean we need to like subdivide this to 4. So these are the quarter points. So if we divide this to L over 4, L over 4, L over 4, L over 4. So these are the 2 moments. And M3 is the design bending moment at the midpoint of the segment. So here M3 will be equal to MM in this case, because M3 is here. So here is M3, here and here M2 and M4. This is just an example for this case. Or the final method to find alpha m is a value obtained from elastic buckling analysis with clause 5.6.4 except for the subsegment formed by intermediate lateral restraint. So we can ignore this for now. So we can focus on these three. Okay. So these are the values of alpha m. The next parameter is, so alpha m is okay. The next parameter is alpha s. Alpha s can be calculated using this formula. Where alpha s equal to 0.6 ms squared over MOA plus 3 all under root minus ms over MOA. So in this equation, we can know ms because ms equal to F yield times Z effective. But what is MOA? MOA shall be taken as one of these. MOA equal to MO, where MO is the reference buckling moment, or MOA can be calculated using the value determined from an elastic buckling according with 5.64. So we use first one. So MOA equal to MO, where MO is the buckling reference moment. The buckling reference moment can be determined using the following equation. So the reference buckling moment MO shall be taken as this equation. So MO equal to pi squared EIY over L effective squared all times G times J plus pi squared EIW or I warp over LE squared all under square root, where E and G are elastic modulus or moduli of steel. For your information, E equal to 200,000 MPa and G is 80,000 MPa. E is the elastic modulus or Young's modulus. G is the shear elastic modulus. And can be found in the standard in clause 1.4, which is the definition of the material. IY, J, and IW are section constant, also from clause 1. This can be found in the tables, design capacity tables, where IY, inertia about Y, J is the torsional inertia. So IY, inertia about Y axis. J is Ix plus Iy, which is a polar moment of inertia or inertia that resists torsion. Iw is warping modulus, which is also a probability of material. So this all are like can be so all these values you can write here. E by Iy, G, J, E, Iw, all are and also by all are like constants or can be added easily. So what we need to calculate here only L effective. L effective, which is the effective length determined in accordance with clause 5.6.3. So what we need to calculate here is the effective length of B. Okay. So I'm just trying to look for L effective here. So here is the effective length required to calculate. So L effective is needed for M naught. Hello Gulhar. And hello Samuel. Have you joined us? Can you hear me clearly? Okay. Anyways, session are recorded, is recorded, sorry, and will be uploaded to the Blackboard. Okay. Okay. Anyway, we was in the procedure of determining the member capacity of beams without full lateral strain, and we have reached to that we need to calculate the parameter or the value of M naught, which is the reference buckling moment. And we calculate M naught, we need L effective, which is the effective length of the beam. So the effective length of the beam the effective length of the beam, L effective, is determined as follows. L effective equal to KT times KL times KR times L. L is the beam or segment span, which is the length of the beam. This is easy one. KT is the twist restraint factor given in table 5.6.3a. KL is the load height factor given in table. KR is the lateral rotation restraint factor given in table. So tables 5.6.3, 1, 2, 3 are used to calculate the factor needed to calculate L effective. Okay. So if we go to the factors here, the twist factor, twist restraint factor KT. KT for FF, FL, LL, FU. These symbols are explained in the beginning of the lectures for the restraint of the supports. So in this beam, or in this case, we mentioned that the beam is fully lateral restrained at both ends. So this means for this case, it is FF, which is 1. So if the beam is fully lateral restrained at supports, or FF, so you can take KT as 1. For other cases, so you can use this formula. Okay. The second table we need is table 5.6.3b for the load factor KL. Again, for the segment with segment FF, this is the restrained arrangement. So for the shear center for the shear center KL will be 1. For the top flange, if the load at top flange, so this means the load position. If the load applied on top flange, so these are the values. If the load applied at the shear center of the beam, so this is the value. As you know, if we have a section like that, so the load can be applied here. For other sections, like let's say channel, for the channel, because it is monosymmetric, so it has two centers. This center is called center of gravity, and a center here called shear center. So here, if the load here applied, let's say here on top flange, so you can take the value from here. If the load here applied at the shear center, so you can take the value as 1. Okay, so this is an explanation of the value of KL. The next value is the lateral rotation restraint factor, KR, also depend on the restraint arrangement. End with lateral rotation restraint if you have any both lateral restraints or one or none, so you can take the value from here. So all these values just to find L effective. Okay. There's also some notes here. L can be taken as a segment length for segment without intermediate strain. So this means that L is the beam span or the beam length, as we mentioned. The other option or the other case is the subsegment length for subsegment formed by intermediate length. So you can ignore this too and also and only take L as the beam length. Okay. So after we get L effective, if we go back to our calculations, so now we know L effective, so we can get M naught. So after M naught, we can get alpha S. After alpha S, we can get M buckling. So finally, we can get M buckling. M member capacity, MB. So MB is again lambda M, lambda S, MS. And all this procedure just to find MB. Okay. So this is the important case we have here. This case, you can read about this case. This if the section is very close section. If you have very close section, you need to follow this procedure. Okay. Okay, this one is for segment only restrained at one end, like cantilever. As you know, for cantilever, it is only restrained at one end. So for cantilever or member restrained at one end, the nominal member moment capacity (MB) of a segment unrestrained is at one end, and at the other end, both are fully or partially restrained, laterally continuous or restrained against lateral rotation, shall be determined as follows. Equation 5.6.1 with MOA equal to MO, as we have done, or this procedure. So MB equal to alpha S times MS, and cannot be less than MS. So this is the member capacity for cantilever, which is restrained at one end and unrestrained at the other end. So this end is restrained and this end is free, so it is unrestrained. Okay, so here alpha S has different formula. Alpha S has different formula here for member restrained only at one end. Okay, this means here we take M alpha M as 1. If you look back at the formula, it was alpha M times alpha S times MS. Here this means that you can take alpha M as 1. Okay, and the other difference is that here it is not MOB, it is it is not MOA, it is MOB. So this also again another difference here, where MS is the nominal section capacity and MOB is determined by elastic buckling analysis in according with 5.6.4. Okay. If you don't want to calculate lambda MOB, so you need to use the first procedure here, which is the previous procedure we have done with MOA equal to MO obtained from equation 5.6.1.1 and the appropriate value of alpha M. So here the first one, the procedure will be alpha M alpha S times MS. This is the equation. But here the change is alpha M here will be taken from this table 5.6.2. So for cantilever, you can use same procedure, but only use this table for alpha M for cantilevers. Okay, as you can see here, values of alpha M can be taken as 0.25, 1.25, and 2.25. Okay, so this all are the required thing to calculate the member capacity. Again here, the member capacity of members without fully lateral restraint. Okay, and these are some capacity tables for this for universal beam grade 300, and this is the chart, and this also table for universal column. This is just an example of the tables. Have you been able to use the charts and find the charts in the quiz? Okay, that's good. Thank you, Scott. Okay, the next point we will go through is the design structure member subject to combined actions, or in some books are beam column members. Because beams are subjected to moment, column normally are subjected to normal. So combined actions means members subjected to normal and moment, which are or can be found in frames or portal frames, because all the members in frames are subjected to moment and normal, or combined moment and normal forces. Here as well, you can go through this an example of the loading of a beam. Sorry, of like frame member. Let's say this frame members or beam column members. What you can see here, we can see that the first one here, let's say this member is subjected to a normal force N and a moment about My, about y-axis My, or we can call it minor axis bending. So the first column is under Mn star and My star. The second column also subjected to normal force and bending moment, but this bending moment about Mx, so it is a major axis bending. So this member is subjected to N star and Mx moment, or a moment about X. The third one is subjected to normal force and major axis bending mx, but it is also subjected to flexure torsional buckling. So this one has N star, mx star, and flexure torsional buckling. The flexure torsional buckling is called also global buckling or global behavior because all the column, the length of the column has been affected by, like, the total length has buckled. As you can see here, we have moment about mx here, but the buckling happened about the minor axis my. So this can be translated to my. So in this case, we can call it like m about x and m about y, which can be equal to or equivalent to biaxial moment. So we have moment about x and a moment about y. Okay, so here we have to design or get the design action of beam columns. As you can see, you can have normal force in the star, and you can have mx and my. So in some cases you have the three. This is the generic case if you have all the possible strain x. Sometimes you can have n and mx only, or n and my only. Okay. So I will go through as well the formulas quickly. So for the section capacity, we have also for these types of elements, section capacity and member capacity. For section capacity, member subject to combined action, we can find it in clause 8.3. The member shall be satisfied these these three clauses. So the first type is uniaxial bending about the major principal axis. So if you have a beam like that or a member like that, so you have x-axis and y-axis. So in this case, we have the moment about the major x. Here, what is the major x? The major x is x-axis. So this is moment about major m about major x or mx. So in this case, where is the uniaxial bending about major x, the following shall be satisfied. So we have mx star should be less than or equal phi mrx, where phi is a capacity table, phi is a capacity factor from table 3.4, and mrx is a nominal section capacity reduced by axial force. So because we have m and n, so the section capacity will be reduced, and the reduced will be mrx. So mrx equal to msx times 1 minus n star over Okay, Rufus, so I will do that. The portfolio question will be tomorrow. I will send them today or tonight and will be ready tomorrow. Okay? See you. No worries. See you. Okay, so this is MRX. So here the section, the uniaxial capacity, uniaxial bending moment about the uniaxial bending about the major principal axis mx star, sorry, should be this value, where mrx is msx times 1 over n star minus n 1 minus n star over phi ns. Okay. These are some cases here. So this is the value of mrx. Alternately, for doubly symmetric I section or rectangular square hollow section, which are compact. So if the section is compact, mrx can be calculated as one of the following. So this is the general one, but if in some cases you can use the following values. So if the section is compact, so you can, for compression members, so compression members means n is negative or compression. So, and kf is equal to 1, and for tension member. So for normal compression and kf equal to 1, or for tension member. Tension members mean normal is positive. So mrx can be determined using these values. 1.8 18 msx times 1 n star over phi ns. The other option or the other case is compression member where kf is less than 1. So if kf less than 1 and n is negative or compression, so this will be the value of mrx. So the value of mrx equal to msx 1 minus n star over n phi ns times 1 plus 18 82 minus lambda w over 82 minus lambda wy. Okay, where lambda w and lambda wy are the values of lambda E effective and lambda E yield for the web. This is what we have calculated earlier. Lambda E equal to B over T times root F yield over 250. Okay, and MSX and MSY are nominal section moment capacity about x-axis and about y-axis respectively, where MSX equal to F yield Z effective X, MSY equal to F yield Z effective Y. Okay. So, and NS is the nominal section axial load capacity determined according with 6.2 axial compression or 7.2 for axial tension. Okay, so all these are values from previous lectures because this lecture is a combination between compression members and bending or flexion members. So this was for major axis. The second case is the minor axis or MY. So here, if we have uniaxial bending about minor axis. So again, to know what is the minor axis bending, if we have this beam and we have this is x axis, this is y axis. So what is the minor axis bending? This is the minor axis bending MY. So MY is the minor axis bending. So where we have uniaxial bending occurs about minor axis or y axis, the design bending moment M star about the minor axis shall be this formula. The similar formula, but My, where phi again is the capacity factor. Phi usually equal 2.9, but you have to refer to this table to if there is another case. And MRY is the nominal section moment capacity reduced by the axial tensile or compressive force. So here MRY equal to same formula, but MSY instead of MSX. Alternatively, MRY may be calculated as one of the following. For doubly symmetric I section, where R compact. So for all compact section and symmetric I sections, the value of MRY can be taken as follows. It is a quite similar value of the previous case, but here it was 1.18 instead of 1.19. Okay, the second option for rectangular or square hollow sections and compact, MRY is same value here. But don't remember here there is a square. So these are the values of MRY for these two cases, or these two special cases: compact section, compact I section, compact rectangular, and hollow section. Okay, so these are the two cases we have. The third case, if we have a biaxial bending. For biaxial bending, what is the biaxial bending? If we have a cross section, let's say I beam, so you have two axes, x-axis and y-axis. So we can have M about x-axis, mx, major bending, and M about y-axis, my. So this is called biaxial bending. So we have mx and my. The case here, the equation should be satisfies this one. So we have n star over phi ns plus mx star over phi msx plus my star over phi msx should be less than or equal 1. Okay, there is also some other option for some special cases. For doubly I section, rectangular hollow section, which are compact. So for compact section, the value, the value or the biaxial value where mx and my with compact section. So mx star over phi mrx and the to the power gamma, okay, should be less than 1. Where mrx and mry, we have calculated them earlier, and gamma is 1.4 plus n star over phi ns and should be less than or equal to 2. Okay, so in the previous part, we have finished the section capacity of members subjected to compression and combination of compression and or normal force and bending moment. And now we are looking at the member capacity of members subjected to combined action according to clause 8.4. So again, the combined actions are normal forces and bending moment. So we have N and M, which can be found in frames, members in frames. Okay, so here the member shall satisfy these three clauses for compact and for like 8.42, 8.43, and 8.44 as appropriate for member bent about major principal axis only, where there is sufficient restraint to prevent lateral buckling, or member bent about minor axis. So you can read this two conditions. But for the main one we need is 4.2. This is in plane capacity. So each one of them is for a case coming. One is in plane elastic analysis. One is out of plane elastic analysis. One is in plane elastic analysis, and so on. So you can decide which one is appropriate. But for case, we have in plane capacity for elastic analysis. First of all, if we have a compression member, so we are looking at in plane elastic analysis. So for compression member, so normal force is negative or compression. A member bent about principal axis shall have sufficient in-plane capacity to satisfy the following. So M star, the applied moment should be less than or equal phi mi, where again phi is a capacity factor from table 3.4, and I have added the capacity factor somewhere here. So here is the capacity factor 3.4 phi. So for members subjected to bending, this all 0.9. For members subjected to compression, also 0.9. For members subjected to tension, 0.9. For members subjected to combined action, section capacity or member capacity, 0.9. So for our case, phi is equal to 0.9. Where M star is the design bending moment about principal axis, where if this our cross section, this is X and Y. So this is a major bending capacity, major axis, and this is the moment about major axis. And MI is the nominal in plane member capacity, member moment capacity. So I is indication of in plane. So in plane, MI equal to MS times 1 over 1 times 1, 1 minus N star over phi in C. Okay. So MS, nominal section capacity, as usual, for bending about principal axis. Again, MS equal to F yield times Z effect. So we have used this before. N star is the design axial compressive force. NC, what is NC? NC is the nominal member capacity in axial compression determined according to clause 6.3 for buckling about the same principal axis. So we have to calculate NC for buckling about X axis with the effective length K effective taken as 1 for both braced and sway members. So K equal to 1. Unless a lower value is calculated for braced member from these clauses. Okay, so again here, NC is the member capacity in axial compression. So this is NC. Also, here is another alternative for MI for doubly symmetric I section and rectangular square hollow section, which are compact. So for compact again section, I sections, MI is equal to MS, all this formula, just to find MI. MS 1 plus beta M over 2 all cubed times 1 times minus N star over phi NC plus 1.18 times 1 plus beta M over 2 all cubed times root 1 over N star times N star, sorry, 1 minus N star over phi NC. And there is a condition here that MI cannot be more than phi MRX or MRY as appropriate. So if it is major axis or it is minor axis. Okay, where beta M is the ratio of smaller to larger bending moment taken as positive when this, we have used this before, taken as positive when the member is bent in reverse curvature for members without transverse load, or value determined according with for members with transverse load. So beta M, if we have here M1 and M2, beta M equal to M1 over M2, where M1 is the smallest. Okay. And what is MRX and MRY? MRX and MRY are the nominal section capacity about the appropriate principal axis determined in accordance with clause 8.3. We have just calculated this. So here, all this was for compression member. For tension member, because there is no buckling in tension member, so it is a little bit different. So for tension member, a member subjected to design axial tension N star and design bending moment M star shall satisfy clause 8.3. In other words, member capacity is not applicable for this section. So here, if we go to clause M3, M8.3, which is the section capacity, where is the section capacity? So here is the section capacity. So here it will be MRX directly. So here M star should be less than or equal MRX. So this means that there is no member capacity for members subject to in tension and M, because there is no buckling. So if no buckling, so the member capacity doesn't affect, or there is no buckling effect. This all was for the in-plane capacity. The next is out of plane capacity, which is clause 8.4.4. So for out of plane capacity, again, we have compression member and tension member. For compression member, a member subjected to design axial N star and design bending MX about its major principal axis X axis, which may buckle laterally. So short shall satisfy 8.4.2 and also the following. So here, MX star should be less than or equal MOX star, where O is indication of out of plane. Where again phi equal to 0.9 and MOX is a nominal out of plane member capacity, or MOX equal to the following, where MOX equal to MBX times 1 minus n star over phi n c y, where MBX is the nominal member capacity of the member without full lateral strain and bent about the major principal axis determined according with clause 5.6, which we have done earlier today. MB equal to M alpha S, or sorry, alpha M, alpha S, MS, and less than MS. This is the member capacity we have talked about earlier, where NCY is the nominal member capacity in axial compression determined according with clause 6.3 for buckling about the minor principal axis. You have to notice that here is X, here is Y. That's why here NCY is the buckling about the minor principal axis, Y-axis. Again, here we have some other special cases for members without transverse loads, which are compact, WI section, and fully or partially restrained at both ends. Have a form KF of 1, determined according with clause 6.2.2. MOX may be calculated as follows. So MOX can be, in this case, if it satisfies all the previous cases here in this part. So MOX is equal to alpha BC MBXO 1 minus n star over phi NCY times 1 minus n star over phi NOZ less than or equal MRX, where 1 over alpha BC equal to 1 minus beta M over 2, 1 plus beta M over 2 all cubed times 0.4 minus 0.23 n star over phi NC, where MBXO is the nominal member moment capacity without full lateral strain and with a uniform distribution of design bending moment so that alpha M is unity determined in according with clause 5.6. And NCY is the nominal member capacity determined according with 6 buckling about minor axis. Beta M is equal to M1 over M2. NOZ is the nominal elastic torsional buckling capacity calculated as follows. So NOZ is using this equation. G times J, where G is 18,000 MBA. J, the polar moment of inertia. E, 200,000 MBA. I warp, LZ, and IX, IY over A. So E and G, elastic moduli. A, IW, IX, IY, J, section properties using capacity tables. LZ is the distance between partial or full torsional restraint. So LZ is the distance between restraints. Okay, so all these procedures just to find the member capacity for or out of plane member capacity for compression member. For tension member, for out of plane, because the buckling could happen out of plane. So a member subject to design axial tension and design bending moment MX about its principal axis, which may buckle laterally shall be satisfied as follows. So here mx should be less than or equal phi mox, where phi is equal to 0.9. MOX is a nominal out of plane member moment capacity, where MOX is equal to MBX times 1 plus N star over phi NT, and less than or equal MRX. MBX is a nominal member capacity. Again, MBX is equal to phi alpha M alpha S M S. NT is the nominal section capacity in axial tension. MRX, nominal section moment capacity reduced by axial force, determined in accordance with 8.3.2. And here is again the value of phi, the reduction factor or capacity factor. So we have finalized the out of plane and in plane capacity. The last one is the biaxial capacity. The biaxial capacity again means if we have both buckling or moment about the two principal axes, x, x, y, y. So we have mx and we have my. So for first of all, we have the compression member. So we have compression member. So a member subjected to design axial compressive force and design bending moment, my, about major and minor x, shall satisfy the following. So we have this formula for biaxial. So we have mx star over phi mcx all to the power 1.4 plus my star over phi miy for the to the power 1.4 should be less than or equal 1, where phi is equal to 0.9, mcx is lesser of the lesser of the nominal in plane capacity mix and the nominal out of plane capacity mox. So mcx is one of mix or mox, the smallest or the lesser, for bending about the major principal axis determined according with these two clauses. MIY is the nominal in plane moment capacity determined according with clause 8.4 for bending about minor x. So MIY is the in plane moment about y axis. Okay. So this was for the compression member. For tension member, a member subjected to design N star tension and design moment mx and my about m major x and major xy shall satisfy the following. So this is the formula: mx over phi mtx plus my over mry all to the power 1.4 and 1.4 should be less than or equal to 1, where phi mtx is the lesser of nominal section moment capacity mrx reduced by axial tension, and the nominal out of plane MOX reduced by axial tension as follows. So this will be again the lesser of MIX and MOX for this case. And MRY again, it is the nominal section capacity reduced by axial tension determined according with 833. So this is MRY. Okay, so this is the lesser of these two, in plane and out of plane. And MRY is the nominal section capacity. So this is all cases for the member capacity. So if we like arrange them, so we have 6 cases of member capacity, 2 for each, 1 for compression and 1 for compression, 1 for tension. So if we summarize what we have here, so we have member capacity of beam columns. We have major axis bending, minor axis bending, and biaxial bending. In this one, we have compression member and tension member, compression and tension, and compression and tension. So we have 6 cases of member capacity for combined action members. Okay. So this all the formulas we have in the design of members subjected to combined actions. And here in this section, the further note is a summary of all the procedure we need to design the members. Sorry, not this one. Here's the procedure summary. So this one is the procedure summary for design all the members. Okay, so you can have a look on this one, and this will be like a summary of the design procedure for all the cases, and you can follow when you solve an example or you are designing a frame or something like that. Okay, do you have any question about this? Okay, so I will